Okay, YouTube, in this video we're going to introduce the basic shape and common things about graphs of logarithmic functions by kind of exploring graphs of exponential functions at first. So let's go ahead and take a look at the function y equals log base b of x. And so what I want to do is I want to kind of point some things out there. There's a little bit tiny font over there. So we say y equals log base b of x. The first thing that I want to point out is if we were to rewrite this in exponential form, that is, we have a base of b here, we say b to the power of what turned into x is essentially what we're saying here. So b turns into x by taking it to what power? Well, according to the definition of a logarithm, we took it to the y power. And so the thing that I want to point out first and foremost is essentially this. This right here is what we are certainly used to when it comes to an exponential function. We say y equals, and even more general, we say a times b to the x. But this is our exponential function that we're used to right here. Well, we say that the logarithmic function is just having its x and y switched around. So what we're going to start with is this, that logarithmic functions and exponential functions are inverses of one another. These are inverses of one another. And the reason why I want to bring this up is because recall that with a domain and a codomain here, we say x and we say f of x, or we could say y over here. We have a bunch of x values going through a function f and landing over here in this domain or this range. What our inverse function is designed to do, in this case it's going to be our log function, here it's going to be our exponential function, but the logarithmic function basically takes our output. We already know what we're going to get, for instance, and it says, well, you know, what was our original input? So it sends it backwards. And so that being said, we know that graphically a few things are very true about these. Starting with, they must be reflected about this line y equals x if their domains and ranges switch. Also, every point xy that's on the initial relationship is going to be the yx point on the inverse relationship. So what I want to do is I essentially want to use our common knowledge of exponential graphs, which basically, you know, they have this basic shape here, to kind of come up with what a logarithmic graph would look like here. Instead of having a horizontal asymptote at the, you know, the x-axis, it would be a vertical asymptote at the y-axis. Instead of going through like this 0, 1, usually it goes through 1, 0. And this grows really quickly. This grows fast, our exponential things. So when we draw a logarithmic thing, which we'll complete some tables and draw here, but this would be what a logarithmic graph looks like, and it grows more and more slowly as it goes more and more to the right. So here's what we're going to do. It says to sketch the graph of y equals log base b of x, we're going to use the fact that these are inverses of exponential functions and have domains and ranges that are switched, and also have graphs that are reflected about the line y equals x, this slope of 1 and intercept of 0 thing. So what we're going to do is this. We're going to graph y equals 2 to the x, and then down here we're going to graph y equals log base 2 of x, okay, both with a base of 2 here. And so our initial values that we're plugging in, let's plug in a few here. We say if I plugged in 2 to the 0, I get 1. And we say if I plugged in 1, I get 2 to the 1 is 2, and 2 to the 2 is 4. So these points are on our graph here. We definitely know that 0, 1 would have been one of its points because, well, its a value here is 1. We didn't list it, but we say 1 is our intercept. We say 1, 2 is on the graph, 2, 4 is on the graph, and we can see that it's picking up speed here. And also 2 to the negative 1. If we said 2 to the negative 1, remember that's the same thing as 1 over 2 to the positive 1, or a half. So we say at negative 1, we're at a half. And if we were to do 2 to the negative 2, we get a positive fourth here. So we know that this has an asymptote right there on the x-axis. We say y equals 0. And so here is our y equals 2 to the x graph that is growing more and more quickly. So it grows at a quicker and quicker pace for an exponential thing. So using this fact, I'm going to fill out a table here for a logarithmic graph, and I think this is a good idea. For instance, if I plug in 1 first, I would say then my output would be y equals log base 2 of 1. And so a lot of people, they get confused on this. I say, let's rewrite this into exponential notation where 2 is our base, and 2 turned into 1. We say 2 turned into 1 by taking it to the y power. Well, this y would have to be 0. So we would say, okay, well, the point 1, 0 is on our graph right here, 1, 0. We say, what if I plugged in 2? Now, this is a good one to plug in as well, and the reason why I say this is because the base is 2. So if I plug in a 2 right here, I'm saying, what can I take 2 to the power of to get 2? Well, in other words, 2 to the y power equals 2, then this must be 1. So we get 2, 1. So the point 2, 1 is on our graph. So far I want everybody to see this. We say that 2, 1 is on this graph here, where 1, 2 is on this graph. 1 0 is on this graph, or 0 1's on this graph. 4, and this is going to have to be a 2 here is on this graph, or 2 4 is on this graph. So you can see that all of the points are just trading spots here. And so again, 1/2, if we said log y equals log base 2 of a half. We're saying really, what did I take 2 to the power of to get a half? And we can see that we could take this to the -1, it would reciprocate it. So we'd say that this is -1, we're going to get a -2 here, but essentially we say -1 and an x value of a fourth, we're down to -2. You'll see that we get this graph that actually doesn't have a horizontal asymptote, but has a vertical asymptote at just the y-axis. And instead of, it's going to grow up here like this, but instead of growing quickly, it just grows more slowly and slowly and slowly, because it's doing the inverse thing of what our exponential thing is doing up here. So one thing or some things that we want to point out about logarithmic graphs is that they grow very slowly, okay? As a matter of fact, I would say in general, instead of having a y-intercept, they'll have an x-intercept. And instead of having a horizontal asymptote that's the x-axis, it'll have a vertical asymptote that's the y-axis. And last but not least, remember that domain and range, they switch. So the domain on this is all real x values. If it's an exponential function, if it's, range we're looking at, we say y is greater than 0. Well, down here, when we have something that is logarithmic, notice that the domain here, we say, is all x values, 0, and then on to the right, and we didn't include 0, I guess, that's an open interval. So we'd say all x values greater than 0, whereas the range is all real y values. And so you notice that the domains and range have switched here, as we suspected they would. So using what we know about this graph now, essentially logarithmic graphs, I'm going to draw a few with you here, but we just want to remember that they have, an asymptote on the y-axis and grow very slowly, and they go through 1 0 here if there's no a value. So looking at this here, it says a more general form of our parent logarithmic function is f of x equals, or we could say y equals a times log base b of x, okay? And so essentially, this a value here is going to tell us not what the y-intercept is, like with an exponential thing, but what the x-intercept is. This is x-intercept. We're going to make a table anyways, but I do want to make a note of this. This a value is your x-intercept. So we say h and k are responsible for vertical and horizontal shift when we put those in there, but the parent function is lacking in h and k. So we would want to be able to get really good at graphing the parent function. So let's look at this first here, and we say f of x equals log of x plus 4. What we want to do is sketch this as well as the transformations, and be sure to label the asymptote as well as any points and domain and range. So to sketch this, what I'm going to tell everybody first is this. We're going to graph the parent function. We have y equals log x, and this is going to have to be a log base 10. It's a common log. So we're also saying this. We're saying 10 turned into x by taking it to the power of y. So to make this graph, we're going to say, well, if I'm making the parent function, I can tell you this. It automatically has an asymptote on the x-axis, or the y-axis. We say this is x equals 0. So there's the asymptote. We say asymptote. Okay. As far as x-intercept, we're going to say that it's always the a value out in front of this log. And right now I have 1 times this. And so it's going to go through 1 0, but what I'm going to recommend everybody does anyways, besides just knowing that, is make a table of values. And when we plug in things for x here, we're always going to plug in a couple of values with logs. The first one is 1. We tend to plug that one in here, at least with the parent function. And then we say, how about we plug in the same value as the base? In this case, 10. Because what I know is if I did log base 10 of 1, this must be a 0. And that's where I'm getting this 1 0 from. And if I did log base 10 of 10, I'd say, well, I took 10 to the first power to get 10. So we'd say this is going to be 1. So 10, 1, I'm going to say 2, 3, 4, 5, 6, 7, 8, 9. 10, 1 is going to be this point right here. So you can see that our graph is basically this right here, and it grows really slowly. So we say that this is 1, 0, and this is 10, 1. So what we want to do now is we want to say, well, what would this do to our graph here? This is an h value, and h is -4 as a matter of fact. So everything is going to shift left 4. So this includes 1, 2, 3, 4. This includes the asymptote. Okay, so here's our asymptote. It's now at x equals -4. And then we'd say that this point 1, 0, if you shifted it left 4, it would now be at -3, 0. And if you shifted this point left 4 here, you take 4 off the x value, we say 1, 2, 3, 4. It would be 6, 1. So 6, 1, and we would get the same graph as we had before. So we'd say it looks like that. It kind of overlaps a little bit here. So we'd say the domain. The domain would be all x values greater than -4, where the range is going to be all real y values. Okay, so I'm going to encourage the audience here to actually give this other one a shot here where we have log base 3 of x plus 2. And so I'll get you started. At least do this. Graph the parent function y equals log base 3 of x. And then we'll go back and say that I'll shift everything up 2. The other thing is this. When you graph this function right here, just know that you automatically have an asymptote here. Okay, and we say that our a value up front is going to be our x-intercept right there. So in terms of your table, there are two values you want to plug in, or one, and we'll plug in the base value here. I guess I might as well just go through this. But we say 1, if you plug in 1, log base 3 of 1 is going to be 0 here. And so we have this point already. But we also say that if you plugged in 3, you'd get 1. You would get 3, 1. So this one's not growing as slowly as the other one, but we say, here's our logarithmic function growing very slowly and approaching the asymptote, where the domain is all x values bigger than 0, and the range is all real y values. Okay.